Okay, in this video, I want to start talking about equations of planes and do a little bit of geometry with it. So let's go. Okay, so I want you to kind of think about this in your mind's eye and try to answer the following question. So what are the information that's needed to determine a plane? So plane is like a flat object in 3D space. What information do we need to provide to nail down exactly which plane we're talking about? So if we were talking about a line, we could be talking about 2 points in space, right? If we nail down 2 points in space, then there's only one line that passes through both of those points. So that's one way to describe a line. Another way to describe it would be a point on a line, maybe a directional vector. Just give it a direction and that will determine a line. So similarly, if you're talking about a plane, you need to nail down maybe 3 points in space so that there's only one plane that passes through all of those points. And those 3 points cannot be in a straight line, right? 2 points is not enough because you could kind of put a plane that rotates around that line. Okay, so that's one way to do it. Or another way to do it could be pick a point that's the plane sits on and give it 2 directions that are kind of that spans the plane, right? This direction, and it also goes in this direction, and those 2 vectors together will span a flat space around it. So that's another way to describe a plane. But you could actually describe a plane with 1 point and 1 direction as well. So here's what I'm talking about. So we pick a point, and instead of pointing to the directions the plane spreads in, point in the direction that it's perpendicular to. So pick a vector where the plane makes a 90-degree angle in that direction. And that's enough information to work out exactly which plane we're talking about. So this is the approach we're going to take. So let's say we are given a point in a plane. Let's call that point x naught, y naught, z naught, and a direction that it's perpendicular to. We're going to call this the normal vector. Well, write it as n, and n is going to be some vector ABC. It's the direction that the plane is perpendicular to. Okay, so let's see if we can write down an equation of a plane using these 2 information, right? So what we want is to describe all the points that's sitting inside of the plane. So think of a typical point as XYZ. So so starting at the point x naught, y naught, z naught, no matter which direction in the plane we go, we should be perpendicular to the normal vector. So let's write that down. So if we have a vector from x naught, y naught, z naught to the vector, the point xyz, you can get a vector by subtracting the coordinates. Okay, so that is a vector that starts at the point on the plane and then moving away to some other point on the plane. Okay. And this is, that should make a 90-degree angle with a normal vector. And I named the components of normal vector ABC. Okay. And we know that if you take a dot product, it should be equal to 0. Why is that? So remember, if we take two vectors, we can compute the dot product between them in this formula. But we know that they're 90 degrees. So cosine of 90 degrees or cosine of pi over 2 radians is 0, right? So if they're perpendicular or orthogonal to each other, the dot product should be equal to 0. Okay, I hope that made sense. All right, well, let's compute it. So if the dot product, we multiply components, in such a way, and that should be equal to 0. And voila. So this is an equation of a plane, right? You could write it this way, or sometimes what you could do is you can distribute the components. Sorry, ABC is the components of the normal vector. If you distribute that and collect all the constant terms and then put it on the right side of the equation, you can rewrite the equation in this form. You just put all the constants on the other side and just call it some constant d. So that's another way people might write down an equation of a plane. Okay. So if you know a point on a plane, x naught, y naught, z naught, and the direction that it's perpendicular to, the normal vector, then we could write down an equation about a plane this way. And you lose a little bit of information. You lose the x naught, y naught, z naught, but if you multiply it out and bring the constant on the other side, then it's slightly simpler looking equation, right? So ax plus b, by plus cz equals to d. Okay, so let's do a little bit of geometry with it. Earlier we said if we have 3 points in space, that should determine a plane. So if you're given 3 points, P, Q, and R, we should be able to write down an equation of a plane that contains these 3 points. Okay, so actually I want to use a different color so I don't mess up the notes. Okay, P, Q, R. Okay, so to write it in the formula that we know, we need a direction that's perpendicular to the plane. We could do that by using cross product. So remember, cross product gives you a vector that's perpendicular to 2 vectors. And which 2 vectors is it perpendicular to? Well, if you have 3 points, then we could find vectors between points, right? So vector PQ, I could write down by subtracting the coordinates of Q, subtracting the coordinates of P from Q. So 3 minus 1, negative 1 minus 3, and 6 minus 2. Okay, so that's the vector PQ. And we could also compute the vector PR. So looking at the coordinates of r, subtracting p from it, we get 5 minus 1, 2 minus 3, and 0 minus 2. Okay. And these two are vectors that's sitting inside of the plane. So if it's perpendicular to both of these, it's perpendicular to the plane. Right? So we're going to cross PQ and PR. Two, -4, 4, 4, -1, -2. Okay. To get the ith component, we do the crisscross here. -4 times -2 is 8. And then we subtract 4 times -1. So if you subtract 4, if you subtract a -4, we're adding 4. Let's look at the jth component. We'll do 2 times -2 minus 4 times 4. And kth component is 2 times -1 minus 4 times -4. So we're adding 16. Let's see, 8 plus 4 is 12. -4 minus 16 is -20, but there's a negative sign in front, so it's +20. And -2 plus 16 is +14. Okay, so this is my normal vector. Note that the only thing I care about is the direction of the normal vector. So I could rescale this with any constant I want. In fact, since all of the components are even, maybe I could get smaller numbers by dividing each component by 2. So my normal vector is going to be 6, 10, 7. Okay. All right. And then let's see, I have the normal vector and I need a point on the plane. So I could use P, Q, or R. Let me just use P for fun. And then I can write down the equation of the plane. Seven times Z minus 2. Okay. And that's the equation of the plane. Okay. I could also multiply it all out and collect the constant term on the other side. So 6x plus 10y plus 7z. Let's see. Okay, so there's -6, -30, and -14. So if we add everything together, it looks like we're going to get 50 even. So that's another little bit simpler equation. Okay. Just to kind of check your work, what we could do is we can kind of plug in the coordinates of Q and R to make sure that they also satisfy the equation. So maybe I'll plug in 5 and 2 maybe. So 5, 2, 0. So let's use point R. So if I plug in 5 for X and 2 for Y, so 5 times 6 is 30. and 10 times 2 is 20, and 7 times 0 is 0, and they add up to 50. So that works. And I can also plug in the point Q to check as well. But let's call it good for now. Okay, so let me do another geometry problem. Okay, so let's say I'm given two different equations for plane. What I want to do is find the angle between the two planes. So let's see if I can draw this. So here's my picture one plane. Another plane intersecting it. Okay. And if two planes intersect, so this looks exactly like 90 degrees. Maybe, well, okay. It makes two different angles, right? It makes angle here on this side and angle there on the opposite side. So again, if we're talking about what angles do two planes make, I should be worried that there's two different angles that are valid here. So by default, I'm just going to give the smaller angle. So there's always angle that's acute, so less than 90 degrees, and the other one would be obtuse, greater than 90 degrees. And they add up to 180. Actually, it's possible that they intersect exactly in 90 degrees, in which case there's only one angle, 90 degrees, I guess. Okay, so the thing to realize is that if I want to find the angle between the two planes, that would be the same angle that the two normal vectors would make. Okay, so everything is kind of tilted 90 degrees. But yeah, the normal vectors would make the same angles as the planes intersecting. So, and we know how to compute the angle between two vectors. So that's what we're gonna do. All right, so the normal vector for the first plane is 1, 1, 1. I'm reading the coefficient of x, y, and z here. And if I read the coefficient of the other equation of the plane, 1, -2, 3. Okay. Now I compute the dot product between them. So 1 times 1 plus 1 times -2 plus 1 times 3 is equal to 2. I need to also compute the magnitude. Square root of 3 there. You might have realized by now that I'm really lazy at coming up with equations. So a lot of the coefficients turn out to be 1, 2, and 3s. So I get the square root of 14 quite a bit in Calc 3 class. Anyways, let's see. So I want to compute the angle. So angle is going to be arc cosine of the dot product, which is 2, divided by the magnitude of both of the vectors. Okay, so let me compute them. I think I'm going to do this one in degree mode. So inverse cosine of 2 over, in parentheses, square root of 3 and square root of 14. Okay, so I get the angle 72.02 ... So roughly 72 degrees. So this is the acute angle. I could have very easily gotten the obtuse angle depending on different, like a normal vector that was given. Okay, so that's the one angle. And if I wanted to compute the other angle, I would just do 180 minus this number to get the other number. Okay, all right, so that's one problem. There could be a follow-up equation. So try to imagine two planes intersecting. That creates a line that's inside of the both of the planes. So what is the equation of the line? That's the intersection of two planes. Okay. All right. So to come up with the equation of a line, I need a point and I may need a direction. Okay. So the direction I can get using cross product, right? So the directional vector is perpendicular to both of the normal vectors for the two planes, right? Because normal vector is perpendicular to every vector inside of the plane. So if we take n1 cross n2, I can get the directional vector, and let's call that v, for the line that's sitting inside of both planes. Okay, 1, 1, 1, 1, negative 2, 3. And after that, we also need a point on the plane, but that's inside of both planes, but let's do that later. Okay. Okay, so cross product. Okay, so 1 times 3 minus negative 2 times 1. So 3 plus 2. The jth component will be 3 minus 1. The kth component will be negative 2 minus 1. Okay, so that's a directional vector. Let's make sure, I'm going to take the dot product to make sure this works out to be 0. So yes, this is orthogonal to 1, 1, 1. And it's also orthogonal to 1, negative 2, 3. Okay, so this is the directional vector. Okay, I also need a point xyz that satisfies both of these equations at the same time. Well, there's 2 equations I have and 3 unknowns. So it's actually underdetermined. So there's actually lots of points that satisfies both of those equations. So I'm just going to pick a value for z coordinate. So let's say, I'm going to say z is equal to 0 and plug that into both of these equations. So from the first equation, I get x plus y plus 0 is equal to 1. And from the second equation, I get x minus 2y plus 0 equals to 1. Okay. Now I have 2 equations and 2 unknowns. I can work out what the x and y would have to be. Here, I think what I'm going to do is I'm going to take the first equation and then subtract the second equation from it. So x minus x is 0. Y minus negative 2y would be 3y. And then 1 minus 1 is equal to 0. So y would have to be 0. And I'm going to go back to this equation here. If z is 0 and y is 0, then x would have to be 1. Okay, so the point 1, 0, 0 is sitting inside of both of the planes. So I can plug it in 1, 0, 0 into both of these equations to kind of check that it really does satisfy both equations. All right, so now I'm ready to write down the equation of the line. So we want the symmetric equation. So that's this form, right? And I have the ingredients. This is the directional vector, so that's my ABC. And this is the point on the lines. That's my x naught, y naught, z naught. So x minus 1 divided by 5 is equal to y minus 0 divided by negative 2, which is equal to z minus 0 divided by negative 3. So that's my equation of a symmetric line, which represents the intersection of the two planes. Okay. I hope that made sense. So we're using clever uses of the dot products and cross products to solve these types of geometry problems. We're gonna do more geometry problems next week. So I want you to be able to get more used to these type of geometry problems. Anyways, this is where I end for this video. I'll see you later.